Okay. Well, thank you for me to give this presentation. I want to start with thanking for being here and for the University Côte d'Azur for organizing this, to be physically present and all the work they've put in, for instance, with the room we have here. My name is Jeroen van Tubergen. I'm currently a master's student in computer science at Utrecht University. And here I'll be presenting work that originated from a bachelor thesis and another project, which now turned into personal work. And I would like to share with you my development process on audio output synchronization using signal analysis. So let's start with the motivation. I'm into interactivity in the sense audio is really interactive. Dancing, singing, we take them for granted, but it's highly interactive. And it's something I personally sometimes miss in the computer landscape. That led me to doing a bachelor thesis on how web applications can actually fit into this space, and in that sense, the fitness of web applications. The title is quite long, but the core idea is, if we want to do any type of audio performance, how fit is the current web? Well, it was quite new to me, so I could basically mention it like, okay, well, the platform is immature, but I think that's too easy. I simply didn't know how to tackle any interactivity, really physical presence, not just remote, not broadcasting, but really on the same spot doing audio activities. And that made me think even further, that I was actually quite surprised it's not there, because our phones are capable to communicate with satellites. You know, insane encryption. There's no problem with communication when you look at a phone. However, if we have two phones right next to each other, on the sound we can hear ourselves, it's not capable of playing along. And that's when I thought, okay, let's start with the most basic example, playing a song together with the phone. So the phone is playing the song. I'm already going a little bit further in talk, but I want to do it automatically, so no manual interaction required. And this could be used, for instance, for an improvisational speaker setup. For instance, here, we'll be using a phone to basically construct a speaker setup. But additionally, think about events on festivals, public performances. It's quite common to use your phone as a lighter, but what if you're actually participating in the sound production? I think it's huge what you can achieve if you really have stable and trustworthy audio synchronization. So we can definitely just play a sound and use network to, okay, let's start play together now, but there's no guarantee. There can be large deviations, and I thought, okay, whatever prototype, the end prototype, it must guarantee an output of 10 milliseconds, and otherwise it doesn't participate. So what existing solutions are there for distributed playing music? Well, there are a few. However, I precisely want to focus on, is it scalable to mobile? The first obvious one, hardwired speakers. That's right here. We're using multiple speakers here. The second technique, but then there's a single agent. So there's one computer that's controlling it all. But with a mobile, there are multiple agents that all handle individually. So once we move towards that domain of separate agents, the solutions usually are manual. As far as I've seen, they're only manual. It's like, yeah, you have to adapt your output latency, just change the slider until it works. And usually as well, they run on apps or programs, which is okay, but we might as well can do it on a website. Because I think if you can run on a website, it's accessible, it's obvious in that sense. You don't have to install additional software. You're not going to buy a mobile phone these days without a browser on it, which allows it for this broad range of devices it can support. So this is the motivation on my work. Now we'll go on to the actual construction and my journey on getting to an actual functional prototype. And I would like to make some notes first. This is my experience. Yeah, I might be sound critical about the Web Audio API, but I actually really enjoy using it. In my opinion, it's well documented. For instance, the main website is, yeah, I just like how it's documented. They give examples, for instance. The abstractions they provide, I think, are powerful. If you consider the platform, there is not really any particular hardware the web browser tries to target. And especially powerful, I think, is for the composition itself. As I will show, I have created a prototype, which I think was not part of the initial use case or goal for whoever made the specification. So that's why I think it's powerful. And additional side notes, I pretty much learned audio engineering along the design steps. And now it's a hobby project. It's not my master thesis. So it's not that academic, and the code quality is as well built in evenings, etc. So first, let's consider two web audio solutions. I think I found two, which in theory should suffice. Let's start with the first one. That's from the Web Audio API. It provides an estimation of the output latency of the current audio context. The estimation, I think, is a tricky part, like how precise. The documentation itself doesn't give this estimation, but if it would be very near the actual truth, that would be sufficient to get your output and probably synchronized. There's just one additional requirement. The network activity must be fast. Otherwise, you could still be deviating in a network speed. And there's another problem. It's not that widely supported at the moment. I should have put it in there. Sorry. I think this picture is of last year. It might be updated by now. If so, my apologies. And the second, very promising, the timing object API. If the API works, it will provide synchronized playback of multi-device linear media. Basically, this is the solution. There would be no need for a prototype. It's just plug and play. It solves it completely. But at the moment, they mention it's not, it's still in the specification phase. So it's not usable at this moment. Okay, so that's that part. Let's go to the development history. Before I started my thesis, I actually tried to make a prototype with the course Human-Computer Interaction. That was still my bachelor at Leiden University. It didn't work. I was, as you will see soon, it was completely manual and too naive. Afterwards, in 2020, I went to an improved method, which actually started detecting the signal. The sync for a single device took minutes. It worked only on my device. At Utrecht last year, I managed to build an optimized analysis function which afterwards wasn't necessary. Still, it worked much faster, and it really felt like, okay, this is possible, this is usable. But again, it only worked on my device, and only now it is really getting on a point where it's for practical use. And sync can be done in 10 seconds. It starts up and it can sync. So why is it difficult? I start with this picture. There are basically 4 timers that are incoherent with one another. There has to be a common time. I'm going for the centralized approach, and that's the server time. And for some way, we must end up all the way to the right at the audio time. And once we manage to get all those relationships, we have to realize the audio time will drift. And the drifting is quite problematic. Because, so I've put here inconsistency, inaccuracy, and imprecision. Let me modify that a little bit more. So the timer differences, that's the inconsistency. The audio timer that drifts, that's the inaccuracy over time. So it might be accurate now, but it's not accurate in a minute. The sampling, well, depending on the technique, it's imprecise. Actually, if you're using the get output timestamp, the latest edition, it is precise, but that's only in my last prototype used. And the media stream input timestamps, so when you're recording for the analysis part, they tend to throttle if you're doing anything on the main thread. So, or the audio worklet. So that's causing as well inaccuracy. And the overall audio path is unknown. We cannot, as I've told before, we do not know. Yes, I see a question. I have 3 minutes left. Oh, okay. I thought that was a bit more. Sorry. Audio output constant. So I assume audio output latency is constant. We use a single device for measuring, and we simply have internet connectivity. There are multiple elements in this design. For instance, all the steps. I only focus on the timestamp, attaining the timestamps and their correctness. So first prototype, that was in 2019. Well, it basically required manual interaction. Let's skip that one. Prototype 1 was getting more interesting because now we're actually doing signal analysis. But it took a snapshot of time because processing was that slow. If we had to record 5 seconds, I had to wait 40 seconds because it worked in the time domain, the analysis, and not in the frequency domain. Prototype 2 is the same story. It's also in the time domain, but it ran on the GPU to do the cross correlation. So that was heavily parallelized, and therefore it worked. But the main thread was hanging once in a while, once it was buffering to send it to the GPU. And that caused to hang the main thread and throttling the timestamp events, which was quite problematic to stabilize and get proper times. And the current version, it basically, we use the audio worklet node. We forward it to the main thread just so we can forward it afterwards to the, oh, sorry. To the audio worklet thread, to the main thread, to a worker thread. And there we do all the processing, and then we return the result, which we use. So yeah, this is the development. And there is now currently a working prototype. It's called Your Terms of Service. Brian Barth, my colleague in this project, he will be presenting the talk after the talk, this one. And it's running in the university building yesterday and tomorrow, because today we're not on site there. Maybe it's fun to show a demo of that really quick. Just to show you how the syncing goes. It's not that clear. And they're all the same device, but we're not cheating here. They're actually synchronizing. We could have faked it in that sense, like, oh, they're all the same device. Let's just assume they have the same output latency. But here you can see the actual process that they're completely syncing. So there's a microphone in the middle of the laptop, and you see per device they're making a sound for the signal analysis, and one by one they manage to obtain a proper output latency to be in sync. Okay. So future work, much to tell about. Unfortunately, it's time. So I want to thank you for your attention. Are there any questions? I as well could like show a little demo, but it's better if everyone shows indeed tomorrow to see the prototype.
We have time for one question.
Oh, I had a quick question. Hi. So I'm wondering, is it a set it and forget it kind of thing? So you initially have your synchronization step and then it's going to keep staying in sync? Or is there a constant processing to make sure it doesn't drift over time?
It has to sync only once.
Okay.
So we do not know about the input latency nor the output latency. So if you have a single device, they're all syncing against. They have to sync once and they all stay in sync. We can walk out of the building, you can go home, and 2-3 hours later, it should still be in the exact same sync. Yeah.
Thank you.
One more question here.
So you mentioned that the goal is to get the right latency on each device. Does that mean that, for example, if my phone for some reason is 15 milliseconds behind everyone else, all the other phones in the room will get some delay to match mine? Or is it more complicated than that?
Okay, so basically everything is scheduled 1 second to the future. So if your device is having 15 milliseconds extra latency, it will schedule everything 15 milliseconds earlier. In that sense, it's not that well organized to have an exact latency. It's basically they almost play at the same time. And that's somewhere in the range to 1 second to 2 seconds. That's a safe, yeah.
Yes, thank you very much.